That's some of the theory behind the operative temperature. Now, we'd like to show you how it actually can be measured and to demonstrate some principles for how operative temperature behaves under natural conditions. We're going to start with a demonstration of how radiation and convection affect operative temperature. We're going to build some simple operative temperature thermometers using simple physical models, in this case copper spheres of different sizes, painted either black or white. By using spheres, we are avoiding the complications of shape. We'll take up that complication soon enough, but for now, let's just stay with spheres, because they let us concentrate on the effects of size and color and their interactions with radiation and wind. In the video to follow, we'll demonstrate to you how to make an operative temperature thermometer from these simple models, and how to set them up to follow their operative temperatures through the course of a day. As you watch, I want you to keep 4 things in mind. What do you expect the effect of color to be on operative temperature, and why? What do you expect the effect of size to be on operative temperature, and why? Will the effect of size on operative temperature be the result of a changed interaction with radiation, or with wind, or with both? And finally, what should the effect on operative temperature be of being close to the ground compared to being high off the ground, and why?
The operative temperature is a measure that integrates solar radiation and convective heat transfer associated with wind speed and air temperature to estimate a meaningful environmental temperature for a body of some shape. To begin with, we'll consider a simple shape, the sphere, because this lets us avoid problems associated with orientation to the sun. We'll deal with orientation to the sun and shape issues later. We're using hollow copper spheres because copper is an excellent conductor of heat. The spheres can be air-filled because the integration of radiation and convection takes place at their surface. What goes on inside the sphere is not important for now, although it is important for reasons that we'll consider later. Our model spheres are the copper floats that are commonly used to set water levels in tanks such as toilet cisterns and well points. You can obtain such floats from plumbing hardware and agricultural supply stores. For these measurements, we are going to use spheres of 2 different sizes, one with a diameter of 15 centimeters and one 25 centimeters in diameter. To start with, let's calculate the surface areas and volumes of these 2 spheres. Surface area of a sphere is 4 times pi times the square of the radius. We know the diameter and the radius is half that, so surface area is pi times the diameter squared. For the 15 centimeter sphere, the surface area is 707 square centimeters. The 25 centimeter sphere has a surface area of 1,963 square centimeters. The volume of a sphere is 4/3 times pi times the radius cubed. Thus, the large sphere has a volume of 8,200 cubic centimeters, and the small sphere's volume is 1,767 cubic centimeters. Let's now consider the fate of a unit of radiation that falls on one of our copper balls. It could do one of 3 things, and the result must add up to 1 unit. It can either be absorbed at the surface, it can be reflected from the surface, or it can be transmitted through the body. We'll put transmission aside because that's a rare biological event and it has no meaning for our heat balance equation that we're going to work out from the data we collect. Now, when radiation falls on a black surface, it's absorbed in totality. So its absorptance will be 1. If radiation falls on a totally white surface that's completely reflected, its absorptance will be 0. So the absorptance will be somewhere between 0 and 1, and for biological surfaces, it is between 0.7 and 0.8 approximately. What we'll do now is we'll paint one sphere white with a spray can of matte white paint, and we'll paint the other sphere black with matte black paint. And then we'll do comparisons by measuring the temperatures they reach when exposed to the sun outdoors. As I said previously, we're going to compare 2 balls of the same, this time of the same size, one painted matte white and one painted matte black. So I'm going to take this paint can and I'm going to paint the one sphere matte black to start with. And I'm doing it inside a cover of cardboard to try and protect it from the wind so that not too much of the paint will blow away. And I will probably give it 2 coats. So there we go with the first coat of paint. And now I'm going to hang this on a fence close by, touching nothing so that it will dry by the morning. The second ball I'm going to paint matte white. These will serve as our animals in our first experiments. We're going to hang it by the black wall. To make our measurements of operative temperature, we have to mount our painted copper spheres on something to hold them in the right orientation in space. Making a mount is pretty straightforward and can be done with materials you can get from any hardware store. We start with a center mount, which just consists of a length of iron rebar or an iron dropper, which we pound into the ground with a hammer until it's nice and solid. We then take the length of PVC pipe that we've put our mounts on and slide it over the center stake. That's how we make our mast. We now have to stabilize the mast, which we do with 3 guy lines. We can secure them at the top with a clip made from bent aluminum wire. To secure the guy line to the ground, we pound in another short stake as a peg, again made from iron rebar or dropper, and then secure the end of the guy line to that. Once we put 3 of those in, the mast is stabilized. Now that our copper spheres have been painted either white or black, we need to prepare them for the measurement of operative temperature by implanting a thermocouple in each sphere. For this we need a thermocouple for each, already soldered, a female thermocouple connector plug, a pair of wire strippers, and a small screwdriver. We begin by stripping the insulation from the copper wire that is insulated in blue and the constantan wire insulated in red. We strip off about 1/2 centimeter of insulation and trim the exposed wires so that they're both about the same length. We then remove the cover of the thermocouple plug, exposing the terminals beneath. We loosen the terminal covers with a screwdriver and carefully fit the thermocouple wires under the terminals, ensuring that the constantan wire goes to the constantan terminal and the copper wire goes to the copper terminal. These are marked on the plug. We then secure the wires in place by tightening the screws on the terminals, making quite sure that the bare wires are not touching. Finally, we replace the cover on the thermocouple plug. Our thermocouple assembly is now ready to be fitted into the copper sphere. To insert a thermocouple into the sphere, we will need a drill with a 2mm bit, our prepared thermocouple, a tape measure, a tube of superglue, and some masking tape. We measure a length of thermocouple wire so that the soldered thermocouple junction will be located in the center of the sphere, and we drill a 2mm hole in the side of the sphere near the support. For the small sphere with the 15 centimeter diameter, that's about 7 centimeters. We bend the wire at 7 centimeters and insert the thermocouple into the sphere through the hole as far as the bend. It's a little bit of a tight fit, but that's okay. This will ensure that the thermocouple junction is held securely in place where we want it to be, namely in the center of the sphere. Once the wire is in place, we secure it with superglue and hold the entire assembly in place with masking tape until the superglue hardens. Now we do the same procedure for our small white sphere. We drill a hole in the same place as we did on the black sphere. We measure the length of thermocouple wire necessary to put the junction into the center of the sphere and bend the wire. We put the wire in, again so that the junction will be in the center of the sphere, and we secure the whole thing in place with superglue and a strip of masking tape until the superglue hardens. Finally, we do all this again for the larger copper sphere. We drill a hole and measure the length of thermocouple wire, but this time we need a longer length, about 12 centimeters, because the diameter of the large sphere is 25 centimeters. We bend the wire at about 12 centimeters and insert the thermocouple into the sphere up to the bend so that the junction is positioned at its center. We secure the thermocouple with superglue and a length of tape to hold it in place until the glue hardens. We are now ready to mount the spheres on the mast. We've prepared several spheres to measure the operative environmental temperature. We're now going to take them out and mount them on a mast that is in full sunlight the whole day long. And we'll start by taking one of the small black spheres and mounting it at 2 meters above the ground, that is outside of the boundary layer, in the full flow of the fresh air here. And we'll take another one and mount it at 50 centimeters above the ground so that it's in the boundary layer. This way we'll be able to see the difference between the effects of convection in free-flowing air and air in the boundary layer. We'll now take a white sphere to compare with the black sphere that we've mounted at the top of the mast. Same size as you can see, 15 centimeters, and that will let us tell the difference between the effects of color. Finally, we've got the 25 centimeter ball, which is now being mounted at 2 meters high to examine the effects of size on the operative environmental temperature. And we'll leave these out for a full day. The next step is to connect the thermocouple sensors that are in the center of each of these balls and an air temperature sensor, which is above the main mast, to a data logger that is going to be on the ground besides the mast, inside an insulated box, connected to a computer which will log the data continuously over a period of 24 hours. So first we tie the leads of the thermocouple to the mast, and then we'll lead them down to the ground, and Stuart will plug them into the data logger. So now Stuart is wiring up the white ball. He's wired up one of the black balls, tying it in with a cable tie. We're going to bring them all down the pole together and then plug them into their appropriate sockets on the data logger. Finally, we'll touch up the balls with black and white paint so that we are certain of them being completely painted. In the meantime, I'm going to get hold of this GPS and I'm going to take a reading and put a waypoint so that we know exactly where this pole is, and that we'll be able to use that point to examine the traverse of the sun over the spot during the day and correlate that with the rest of our data.